Welcome back, dear students, to my physical chemistry class. So I continue my class. The definition and unit of K. K is known as the rate constant or the specific reaction constant, the magnitude of which indicates the rate of the reaction. So greater the magnitude of the K, greater will be the rate of the reaction. It is defined as the rate of the reaction when all the reactants are of unit concentration, that is when Ca and Cb equal to 1 or 1 moles per liter, then the rate constant K become equal to the rate of the reaction. That is why K is defined as the rate of the reaction when all the reactants are of unit concentration, hence they are called specific reaction constant. Then the unit of K. The unit of K depends on the order n of the reaction, yet it contains a common unit of time, that is time raised to minus 1 or time inverse, that is in terms of minutes inverse or second inverse. Generally, the unit of K is given by a general equation that is equal to, that is mole raised to 1 minus n liter n minus 1 minute inverse. So remember, the unit of K is given by a general equation or general expression or general formula, that is mole raised to 1 minus n liter raised to n minus 1 minutes inverse 1, okay, where n is the order of the reaction. It can be derived, this expression formula can be derived by a simple equation as given here in the slide, that is Na giving products, rate is equal to minus dCA by dt, that is equal to K into Ca raised to n. Therefore K is equal to minus dCA by dt by Ca now becomes equal to concentration dCA concentration unit, that is mole liter raised to minus 1 by dt, that is minute inverse, okay. Then divide by Ca, that is mole liter inverse, the whole raised to n, whole raised to n, because the term is K is dCA by dt divided by Ca the whole raised to n. On simplifying, we will get the final expression, that is mole raised to 1 minus n liter raised to n minus 1 minute raised to minus 1. So we can check for the first zero order reaction, for n is equal to 0, you put n is equal to 0, and K is simply now become mole liter inverse minute inverse. So for a zero order reaction, the unit of K contains the concentration unit, that is moles per liter, and the common minutes raised to minus 1. So that may be asked for the examination. The unit of a certain reaction is found to be moles per liter minute inverse, or it has the unit same as the concentration unit. Predict the order of the reaction. The order is zero order. Then for the first order reaction is equal to 1, the unit of K now become minutes raised to minus 1 or minutes inverse. It does not contain or does not carry any concentration term. That is also important. For a first order reaction, for K is that is n is equal to 1, K does not contain or does not carry any concentration term, only minutes raised to minus 1. And for the second order reaction, n is equal to 2, the unit of K is liter mole raised to minus 1 minutes raised to minus 1. Then we have to pass on the experimental determination of the rate of the reaction. Okay, there are two, that is measurement of the rate. There are actually two different types of rate that is represented experimentally. One is the instantaneous rate of the reaction as as I already discussed in the form of differential equation, that is instantaneous rate equation, and second is the average rate of the reaction. So we have two experimental rates of reaction. One is instantaneous rate of reaction and other is average rate of the reaction. The instantaneous rate of the reaction is simply, it is represented by a small change in concentration divided by a small change in time. That is minus dA by dt or plus dB by dt, where A stands for the disappearance, minus dA by dt stands for the disappearance of A, while plus dB by dt stands for the appearance or rate of formation of B. That is actually the instantaneous rate of the reaction. Okay. While the average rate is expressed by delta A by delta T or delta B by delta T, you put minus or plus appropriately. If it is reactant, it is minus delta A by delta T, and if it is for product, then become delta B by delta T. It is defined as the ratio of the concentration change at two definite time interval defined by delta T, that is T2 minus T1, while corresponding change in concentration is C2 minus C1. That means C2 minus C1 for A. Okay, that is the average. We have to discuss how it can be measured. Start a reaction with a known initial concentration of the reactants. Okay, then monitor the decrease in the concentration of the reactant or increase in the concentration of the product at a regular interval of time. Using appropriate quantitative method like volumetry, conductometry or spectrophotometry. That is, we have to monitor the decrease in the concentration of the reactant or the increase in the concentration of the product at a regular interval of time using any of the quantitative methods. Then plot the concentration changes against time. The result is an exponential graph. For reactant, it is exponential downwards, and for the product, it is exponential upwards. As shown in the figure, the y-axis is concentration and x-axis is the time. Initially, the concentration of the reactant is very high and is going on decreases with the loss of time for A. And initially, the concentration of the product B is 0 and is going on increases with the increase of time as the time going on like this. And for determining the average rate, you have to select two different time intervals, T1 and T2, for the reactant A, and you have to measure the corresponding concentration as as A1 and A2, and A2. Then you substitute the value here. The average rate is equal to the change in concentration of the reactant A by change in time interval, or the change in concentration of product B divided by time interval, that is minus delta A by delta T or plus delta B by delta T. Okay, you have to remember it is always a positive quantity. Then it can be approximated to instantaneous reaction rates by putting minus delta A by delta T as delta T tend to become 0, that is equal to minus dA by dt. Okay, it is obtained from the tangent of the exponential curve. The instantaneous rate of the reaction can be easily obtained from the graph by drawing a tangent corresponding to a particular time t